Hi everyone, I'm Ryan Alice, and I'm doing a video project on all that I've learned by 28. Next, I'm going to be talking about one of the most important topics of our generation, and that is climate change. Let's start with some of the basic information. It's been shown that an increase in carbon dioxide in an atmosphere traps heat. And when heat is trapped, it makes the temperature go up. So let's look at the amount of increased CO2 in our atmosphere over the last 112 years, going back to 1900. Annual carbon dioxide output has increased from 4 gigatons to 37 gigatons since 1900, almost a 10x increase. And what happens when you have higher carbon dioxide output is that some of that gets trapped and the parts per million of carbon dioxide in the atmosphere goes up. Carbon dioxide parts per million, or ppm, have increased from 293 back in 1900 to 395 here in 2012. And it's been shown that when you have higher carbon dioxide in the atmosphere, temperature goes up. Temperature has risen by 1 degree Celsius since the early 20th century. Now, the key question is that there is some debate about, although actually very little debate in scientific circles, is whether there is a relationship between more carbon dioxide in the atmosphere and the rate at which temperature is going up. And so when you look at the data, when you look at the American climate scientists and the percentage that believe that there actually is a link, what you'll find, as published in a 2010 paper, The Proceedings of the National Academy of Sciences of the United States, that 97% of American climate scientists believe that the recent increase in global temperatures is caused by increased carbon dioxide in the atmosphere. In fact, the IPCC indicates global surface temperatures will increase another 2 to 4.4 degrees Celsius, which is 3.4 to 7.9 degrees Fahrenheit during the 21st century. That's from the Intergovernmental Panel on Climate Change. Now, what would happen if our average surface temperature increased by 5.4 degrees Fahrenheit or 3 degrees Celsius? Well, sea levels at that point are likely to rise by 11 feet. What does that mean? That means that Bangladesh, underwater, more than a third of Florida underwater, 1/5 of New York City underwater. And so can we really accept a world in which these amazing populations, these amazing places are underwater? I don't think so. So what would 3 degrees Celsius mean? Because if we continue on the path we're on now, we're actually on track to see more than 3 degrees Celsius increase just in the next 100 years. Here's just an example of, a descriptive example of some of the things that an organization called Climate Code Red has described about what's likely to happen if we see a 3 degrees Celsius increase by 2100. In the Pliocene, 3 million years ago, temperatures were 3 degrees higher than our pre-industrial levels. So it gives us an insight into this 3-degree world. The northern hemisphere was free of glaciers and ice sheets. Beech trees grew in the trans-Antarctic mountains, and sea levels were 25 meters higher. We just looked at what would happen if the sea level was 11 meters higher, and it wasn't good. Between 2 and 3 degrees of an increase, the Amazon rainforest, whose plants produce 10% of the world's photosynthesis and have no evolved resistance to fire, may turn to savanna as drought and megafires first destroy the rainforest, turning trees back into carbon dioxide as they burn or rot and decompose. This is an example of a systemic effect where you have some increased carbon dioxide increasing a temperature, which then has a secondary ecological effect, which then creates more carbon dioxide, which then increases the temperature further. Another systemic effect is what may happen in the permafrost. Climate Code Red says, as the Arctic continues to warm, melting permafrost in the boreal forests and further north in the Arctic tundra is now starting to melt, triggering the release of methane, a greenhouse gas 20 times more powerful than carbon dioxide from thick layers of thawing peat. The writer Ezra Klein says, there are thousands of gigatons of methane beneath the seas, comparable to the amount of carbon contained in the Earth's coal deposits. And as the Arctic waters warm, some of this methane is likely to bubble up into the atmosphere. And so, I have to say that the current debate does not recognize the true gravity of the situation. While scientists are pretty much aligned of the critical correlation between higher carbon dioxide output, higher carbon parts per million in the atmosphere, and a faster increasing temperature, which will lead to many effects that we just don't want to have to see as a civilization, many people just simply are not yet aware of what is likely to happen if we don't shift to renewables and reduce our carbon output. Increased temperatures are inevitable, and if we don't reduce our carbon output quickly, they are on track to threaten our very civilization and create a destabilized world in which people don't have even access to their basic needs, not just in 1/5 of the world, but maybe even half of the world. And when you have half of the world without access to basic human needs, our civilization could go back a couple hundred years if we're not careful. Now let's look at where we are. So right now, we are at 395 carbon dioxide parts per million as of 2012. Where we stabilize that number will directly and drastically affect the amount of temperature increase and will drastically affect our children's futures. Here's a chart that shows where we end up the correlation between where we end up stabilizing the carbon parts per million from the 395 we are today to where it will be in the future, and then in red, the expected increase in degrees centigrade of temperature on the surface of the planet. If we simply stay where we are today, it's expected that we'll increase about 1.5 degrees centigrade by the end of this century. However, if we go up to 550 parts per million, we're looking at a little over 2 to 2.2 degrees centigrade. Right now, if we do nothing, we're on track for about a 700, 800, 900 parts per million if we continue our current industrial production of carbon dioxide and current use of fossil fuels. At that amount of carbon dioxide in the atmosphere, we might be expecting a 4 degrees centigrade increase in global temperatures, about 10 or 11 degrees Fahrenheit. If that happens, not only we will see sea rises raise 11 or 15 feet, we might see sea levels rise 25, 35, 40 feet. And there's so many connected ecological systems that we might actually end up much worse off and have a truly destabilized world. And so it is so critically important that we as a society figure out how to level off our carbon output below 550 parts per million. Now, there are different views on this. There are some scientists out there that say we actually need to end up under where we're at today, under 400 parts per million. And they may, in fact, end up being right. But definitely, and almost certainly from all the research I've seen and all the scientists I've spoken to about this topic, and particularly over the past 3 months as I've researched it, we have to ensure that we as a society never go above 550 parts per million of carbon dioxide. Now, this is a graph of carbon dioxide parts per million over the last 800,000 years. And you can see that, in general, there's a natural system that regulates carbon dioxide parts per million between 200 and 300. And right now, as we've stated, we're at 395, just under 400. The low emissions scenario that's being considered would take us to that 550 parts per million that we really do not want to go above. But a higher emissions scenario that scientists are projecting take us above 900. We simply cannot allow ourselves as a society to get there. So what are the steps to slow and reduce carbon dioxide output more quickly? This is an issue we all must know about. 5 steps. Step 1, stop subsidizing fossil fuels. We'll talk more about that in just a minute. 2, price in the cost of carbon dioxide pollution cleanup in the actual price of things that create carbon dioxide pollution. 3, invest in renewable energy research. 4, subsidize renewable energy use. And 5, increase energy efficiency. Let's go through each one of these. So, fossil fuel subsidies. Each year in the United States, our government, the United States government, using taxpayer dollars, provides $11.5 billion in subsidies to the oil industry. Those are 2010 figures from the Organization for Economic Cooperation and Development. This needs to stop immediately. It is counterproductive to the future stability of our civilization to subsidize fossil fuel polluters. The second thing we need to do is have a carbon pricing system that prices in the cost of pollution in the cost of things that create that pollution, so that we can use a true market economy to provide market prices instead of the current subsidized economy that is artificially keeping fossil fuel prices low. One of the reasons fossil fuels are cheaper than they otherwise would be is because the external cost, which is called an externality in economics, is not included in the price of the fossil fuels that create CO2 pollution. Third, we need to invest in renewables research. Wind, solar, biofuels, nuclear fusion, nuclear fission have great promise, and we need to be funding more research on renewables. Let's compare how much the United States spends annually on R&D renewables research as a government compared to how much we spend annually on defense. Each year, the United States, 2010 figures, spends $706 billion on defense. Most recently, it was closer to $650 for the upcoming 2013 budget. And according to the U.S. Energy Information Administration, $1.4 billion, about 1/500th of the amount we spend on defense, on renewables R&D. And while I think that investing in our national security is critically important, I actually would argue that investing in renewables research and development is directly aligned with our national security. We will see a world that is very unstable if we don't rapidly move away from carbon dioxide producing fossil fuels in the next couple decades. So let's compare how much we spend on defense, how much we spend on fossil fuel subsidies with how much we spend on renewables as a government. So $706 billion on defense, about $11.5 billion on fossil fuel subsidies, and $1.4 billion on renewables R&D. Now, if anything, if we can simply switch these two figures, that will be a good start. We should 10x our annual investment at least in renewables R&D, if not more, and eliminate our fossil fuel subsidies immediately. Step 4 is to subsidize renewables use. So right now we've been subsidizing fossil fuel production for probably about the last 100 years, ever since the first oil well was drilled in Pennsylvania in 1859. But in order to increase market investment in renewables in the next few years during the critical phase when R&D is conducted, we need to subsidize the cost of renewable energy and use incentive structures to enable the price of renewable fuels that don't destroy the world to be lower than the price of fuels that do destroy the world. Fifth, we need to increase energy efficiency. There are architectural designs now that create efficient buildings that use 1/10 of the energy use that the average building uses. We need to move towards smart design. We need to have a two-way grid in which we not only can produce power at the power point level, but can actually produce a small amount of power at local residences and put the extra power back into the grid so that it can better regulate supply and demand. And we need smart appliances that turn themselves off when they're not being used and use energy effectively and efficiently. I believe that our best bet is investing in clean energy from renewable sources to reduce and greatly reduce the likelihood of the damage that is expected from climate change. Now, a great news is that solar power can produce a lot of the world's energy needs. Now, if we were to want to cover all of the world's energy needs from solar power today, because of the current cost of photovoltaic cells and materials, it would cost about $50 trillion to provide all the world's energy from solar power. That's almost 75 or 80%, 5/7 of the world's global GDP, which is 70 trillion. However, solar power is greatly reducing in cost every year. We're currently seeing a Moore's Law-like effect where the cost of solar power is being cut in half nearly every 18 months. And by 2017, solar power will be less expensive than grid power, which is often coming from fossil fuels. And that is when we as a society reach the critical tipping point. When the solar grid parity effect is achieved, when the cost of solar in terms of the retail cost per kilowatt hour is lower than the cost of grid power, tremendous things can happen. And right now it's about 30 cents per kilowatt hour of solar at retail and 8 cents per kilowatt hour for grid power. By 2017, 5 years from today, it's projected those two numbers will meet, and we will see soon thereafter a lower cost of solar power than the cost of grid power. That is called grid parity, and when that happens, we will see tremendous market forces happen. But our goal, as a society and as a government, as taxpayers, need to be that we must demand that we invest from our corporate energies and our governmental funds to be able to speed up this market effect. So it's a race to grid parity. And in effect, this is our species' moon landing. For this decade, between 2011 and 2020, this is just as important, if not more important, than our race to the moon in the 1960s. This is effectively President Obama's moon landing opportunity. And I think President Obama agrees. In his State of the Union speech in 2011, he said, "We're issuing a challenge. We're telling America's scientists and engineers that if they assemble teams of the best minds in their fields and focus on the hardest problems in clean energy, we'll fund the Apollo projects of our time. At the California Institute of Technology, they're developing a way to turn sunlight and water into fuel for our cars. And at Oak Ridge National Laboratory, they're using supercomputers to get a lot more power out of our nuclear facilities. With more research and incentives, we can break our dependence on oil." President Obama. And in fact, the actual location for this solar research hub is at the Joint Center for Artificial Photosynthesis, not too far away, right here in California. It's the Department of Energy's solar research hub. So let's look at how much energy we're using today and how much energy we'll be using in the future, and where these renewable fuels can come from to make up the difference. Today, humans are using 14 terawatts of power annually, according to Jeffrey Grossman at MIT. And humans are expected to need 40 terawatts of power per year by 2050, about a 3x increase. Now, what are the current sources of energy production? We have fossil fuels providing 86% of global energy, nuclear at 6.5%, hydropower, water power at 6.5%, and solar, wind, and biofuels, effectively renewables, in addition to hydro and nuclear, are still under 1%. And so we have to re-architect this pie chart so that renewables are in the blue, so that renewables are providing more than 80% of our power. If we don't, we're going to continue to pollute the atmosphere in ways that are tremendously detrimental to our children's futures. Now, what if there were microorganisms whose food source were carbon dioxide and their output was fuel? Well, actually, there are. They're called algae. And algae have the potential to be the world's future renewable fuel source. In fact, biofuels produced from synthetic algae are showing great promise right now for renewable fuel production. Algae, by their very nature as an organic living substance, consume carbon dioxide, and they produce fuel, and only require 1/7 the land of corn-based ethanol. Now, that's an exciting field, and particularly a field that we should be funneling research dollars into. Now, what about solar power in the sun? Amazingly, the sun provides enough energy in 1 minute to power the Earth for a year. We have a nearly unlimited source of power out there, at least for the next 4 to 4.5 billion years until the sun goes away. However, we have billions of years of renewable energy right there in our star, right here in our solar system, that can power the Earth for a year, for every minute that hits our surface of our land. What we simply need are better solar technologies that can take in that energy, store that energy, and distribute that energy. That is what thousands of researchers and thousands of companies are working on right now, and over the next couple decades we'll see tremendous innovation to harness algae, to harness biofuels, to harness the sun, and harness atomic power to create a world that doesn't require the use of coal or the use of natural gas or the use of fossil fuels that destroy our environment in order to power the world. I'm a big fan of our society that we built up the last couple hundred years. The standards of living we have as a society and as a species now versus a couple hundred years ago before we discovered fossil fuels are tremendously better. Fossil fuels have done amazing things in the world in terms of enabling us to capture, store, distribute, and utilize energy that has greatly multiplied exponentially the amount we can accomplish as a species. Now, It's time that now that we know the effects of fossil fuels, to move to a fossil fuel-free society made up of renewable resources. In summary, we must quickly reduce our carbon output this decade or face a true human disaster. We must stop fossil fuel subsidies, price in the cost of CO2 pollution cleanup, invest in renewable energy research, subsidize renewable energy use, and increase energy efficiency. If we don't, we will face the consequences. But truly, this is an opportunity. Clean energy is our moon landing, and we in the United States can lead the world. Thank you for watching.